This video is about enthalpy change, which we use delta H to denote, and that is the heat associated with chemical reactions. So we're going to talk about how chemical reactions either release heat or absorb heat in the process. So we're looking at heat or energy change, or as it's properly called in chemistry, enthalpy change, involved in chemical reactions. And so our driving question here is, how do we account for the energy changes that occur in every chemical reaction? And I want to emphasize the wording there, because energy changes do occur. A heat change or an enthalpy change does occur in every single chemical reaction. It's part of the reality when you break the bonds of the reactants and you form the bonds of the products. Since the bonds are not exactly the same, we see they're at different potential energy levels, and so in that process, heat is going to be lost or gained. Okay, so if we examine a theoretical reaction here, x2 plus y2 reacts to make compound 2xy. We could map that out. We could map out the energy going on in that with a potential energy diagram like I've done here. So as you can see, the initial potential energy of the reactants x2 and y2 would be here. So let me kind of highlight that for you. It would be right here. So we see that their initial potential energy is 150 kilojoules per mole. So we start them right here at 150 kilojoules per mole. And then we have all sorts of other data about what's going on here in this theoretical situation. So we see that because the activation energy is 250 kilojoules per mole, that's right here. You can see that's represented here by the hill it has to climb, representing how much kinetic energy must be present in that collision for it to actually react. And then we see it has a delta H, what we call the enthalpy change, of 100 kilojoules per mole. And that's a positive number. Okay, you can see that this number is positive, which means that, as shown by the blue writing there, the final products are going to be higher in potential energy than the reactants. And you can trace them over and see that they're going to be at about the 250 kilojoule mark. Okay, energy is measured in kilojoules, I should mention. So, and we tend to record that as kilojoules per mole in chemistry. So we can see it had a positive enthalpy change. We can see that the final potential energy of the products is higher, and so this is how we would map out the potential energy diagram for this particular reaction. So for this reaction, as it says here, the products were higher in potential energy than the reactants. Thus, heat energy had to have been absorbed in the process. Okay, so if you were actually experiencing this or conducting this process in the lab, what you would feel is you would feel it get colder as it progressed, because heat energy had to be absorbed from the surroundings into the system in order to store extra energy in the bonds of the products. We're also saying here that the bonds of the products have more energy tied up in them than the bonds of the reactants did. So energy had to be absorbed in that process, and we call these processes endothermic. Okay, so if the bond energy is higher at the end with the products and they're higher in potential energy than the reactants, it's an endothermic reaction, and we have a positive delta H. So with regards to that last example, there are several ways, three main ways we can communicate how the heat energy changed or how the enthalpy changed for endothermic reactions. And so you have these kind of three methodologies here. You've got the first way, you can just write the balanced chemical equation as you usually would, and then as an aside, afterwards you can communicate what the enthalpy change was. Okay, so here you see afterwards they just write delta H is 100 kilojoules per mole, and you can see it's a positive value, whether the positive is written there or not. All right, the second way is you can write it as a reactant or product, and in this case for an endothermic reaction, it's always going to be as a reactant. So you can see there that they just say, all right, you got x2 plus y2, and then you have 100 kilojoules per mole of energy. and that's going to create the products. And then the third way is you could write it as a product but subtracted. This I find kind of confusing. I wouldn't recommend this way because you might confuse this with the delta H and think it's like a negative delta H or something. So I really don't recommend this way, but it may be something you see at some stage or another. On the flip side, like what if it's exothermic? What if we have an exothermic reaction? I think we've looked at one of these previous lessons, but that would be a negative delta H, right? And so you would record it as, I would recommend record it one way or the other, either with the negative delta H or with heat as a product. So here it is with the heat energy as a product. I made up another reaction here that theoretically could be exothermic. You'd have either heat energy written as a product, and it's always positive that way, or you would separately write it as a delta H value off to the end of the balanced chemical equation. So just back in reference to that reaction and thinking about what we know about collision theory, we can revisit what happens with the collision of that as well. And my main purpose in doing this is we're going to apply again in the future this concept of the activated complex or the transition state. And so again, we've broken it down now that we're a little more familiar with potential energy diagrams. We're looking at the green zone of the potential energy diagram up here and seeing that this is as we approach, remember that potential energy is growing as the repulsion is growing and they're getting closer together. And so we can see that as they approach, we're rising up in potential energy. Then at collision, we have this very bizarre kind of temporary condition called the activated complex, which is formed right at the top of the hump there. And what's going on in the activated complex is the old and new bonds are partially formed, and that's represented by the dotted lines here, representing where the old bonds were and where the new bonds will be if indeed it is an effective collision and proceeds to products. And then after collision in the blue zone here, we have the new bonds being formed, and you can see the two products X, Y created. So we just want to get comfortable representing activated complexes representing transition states. And so you can draw them like this if you know what the bonds are, or sometimes you could just like draw the whole thing together like this, like it's X square, X2, Y2, something like that, where it's all just mashed together at that moment. Okay, one last thing here to appreciate, and again, it's maybe foreshadowing a little bit into what we'll study in the future with chemical equilibrium. But we have most chemical reactions, whether we realize it or not, I shouldn't say most, but many of them are reversible. So we could have what we would think of as the classic potential energy diagram like this. We have reactants here and we have products here. And so just in summary, we have reactants turning into products, okay, like this. But what we should realize is it could go backwards, and what was the conventional product could turn into reactants. In that case, we would say that from the baseline beginning potential energy of the reactants up to the top, this would be the activation energy of the forward reaction. And then coming at it from the other direction, if we went from the baseline potential energy of the products all the way up to that peak like that, this would represent the activation energy of the reverse reaction. Okay, so what we would see then is that in the forward direction, okay, maybe I should get my color scheme up to snuff here. In the forward reaction, we would see that the products are lower than the reactants, and so this is exothermic. Okay, it would have a negative delta H. Right, the products are lower, so it's released energy. In the reverse reaction, we would see that it is endothermic, okay? You can see that, imagine going backwards, like we are here, that actually in the reverse reaction, we'd have to put energy in because those bond energies are higher back here, okay? So that's endothermic, and it would have a positive delta H. So just something to be aware of when you're going forwards or backwards in some of these reactions. And I guess also just to realize that The activation energy for the reverse reaction would be significantly higher than the activation energy in the forward reaction.